In this lesson, we're having a look at the idea of composite functions. Before we go any further, we need to remind ourselves of what f of x means. So for example, if f of x is x squared plus 2x plus 6, what that means is x is the variable that we're talking about. Okay, if we change that variable to a, for example, f of a would be a squared plus 2a plus 6. If we changed it to f of 2, it would be 2 squared plus 2 times 2 plus 6. So we're pretty familiar with the idea that whatever is in the bracket is what gets substituted into the equation. What we're having a look at today is, what do we do if the thing that gets substituted into the bracket is some other function? What does that end up looking like? And that's this idea of composite functions. With composite functions, we have a very important distinction, and that is an inside function and an outside function, or inner and outer functions. The terminology that we will use the most is this particular one here, and it's called g of f of x. So g of f of x. What we need to recognize is that when it's written like this, what we actually mean is g of f of x. So we've got this outside function, which is g, and everywhere there was an x, we now substitute this f of x function. And this is called a composite function. We need to be careful. Order is extremely important in composite functions. So if we've got g as our outside function, like this one here, so this is g of f of x, that is rarely going to be equal to f of g of x. As we go further through, you may be able to work out under what circumstances are these two things equal, and you should recognize that they are rarely equal. All right, in this example 8.1, we've got two functions, f of x and g of x. You can go through and read the example in the shaded box. It talks about input. I'm just going to go through it algebraically using the two functions that we have here, f of x, 2x plus 3, and g of x, x squared. So first of all, if we have a look at f of g of x, then that's going to be f of g of x. So what we do is we start with f of x. We start with the f function, and then everywhere there's an x in the f function, we substitute the g function. So the f function is 2 times x, but instead of x, we write g of x. And in actual fact, you can write g of x instead of x. So that's the 2x and then plus 3. This step is optional. And then what we're really doing is we're substituting in g of x. So it's actually going to be 2x squared plus 3. And you can see that what we've got here is exactly the same. F of x, here we've got 2 of something plus 3. And it happens in this particular case that the something is the g of x function, which is x squared. So once we've done that, we tidy it up. There's nothing much to tidy up in this particular example except getting rid of the brackets, and that is our answer. With composite functions, you always express them as simply as possible. All right, if we're going to do the other composite function and do g of f of x, oops, sorry, that should have brackets on it, g of f of x, then this time our outside function is g and our inside function is f of x. So looking at g of x is x squared. So we're starting off with not x squared, but f of x squared, because that's the thing that we're substituting into g. F of x is 2x plus 3, and we're squaring that. You can square that via perfect squares expansion to get 4x squared plus 2 times 3 is 6 times 2 is 12x plus 9, and that's our simplified answer. And it's pretty obvious just by a quick inspection that f of g of x, which is 2x squared plus 3, is really very different to g of f of x, which is 4x squared plus 12x plus 9. Like I said, you can read through the example looking at using it as an input, and you should find that you'll end up with the same answers. In the next video, we'll go through some examples.